All right, folks, we're almost done with these videos here for Calc 1, and I hate to say I'm going to be happy when that happens, but I will say it will feel like an accomplishment, right? I think I've put out almost quite a few videos this semester. Has it? I think it's pushing. I hate to say it's pushing 40 videos. So they're if not over already, we're probably at, this is probably the 42nd video that I put out this semester. So it gets to be a little draining, but we only have a few left to go through here, folks, and so I might as well get this one out to you. What I have for you is, and I say that because we're really at the point where in this video, I'm going to present to you one of the most important ideas of calculus. All right. And it's an idea that makes the connection between differentiation and integration, those two concepts. And it's known as the Fundamental Theorem of Calculus. All right. Let me bring up my notes here. Let me get this all aligned. Here's the notes on the Fundamental Theorem of Calculus, right? And to introduce and to actually develop and prove what we're going to see as the statements in this theorem, right? What we're going to have to do is consider the following setup and the areas that we have illustrated in this following setup. All right. What you will notice is we do have function f. F is being defined in terms of the independent variable u and the dependent variable y. X is being reserved for a location along that horizontal axis for u. And as well as x, we have introduced the quantity h to be this horizontal distance that we are in front of x. So that we're a distance of h away from x, and we have this location also in this graph indicated by x plus h. And underneath this curve for f at u, we actually have three shaded areas. One of those areas is shaded here in blue, right? From a to x. One of those areas is shaded gray from x to x plus h. And the third area is the combination of those two that stretches from a all the way down to a plus h. If we start to define those areas individually, the area function will tell me that the area from a to x is what we say is a of x. Right? That would be this area here. And the area function would tell me explicitly that the area from a to x plus h would be the definite integral from a to x plus h for f of u du, which would be like the area function evaluated at x plus h. And if we think about what would be the area of this little shaded region here at the end that I have shaded in gray that stretches for the length of h, right? That stretches from x to x plus h. It would be given by the definite integral from x to x plus h, again, because we understand that the definite integral describes area trapped between the curve. Can I get this? I probably can't. There we go. We can barely see the two. To go from x to x plus h, we understand from the definite integral the area trapped by this function over that interval is the definite integral from x to x plus h for that function integrated with respect to the variable. the independent variable of that function u, where the area function won't tell us explicitly what that is in this case because the area function starts at a. But we can use these two results to talk about this area. This area is the area from a to x plus h. What I might actually do here in the notes to illustrate this, it is this area from a to x plus h for fu du minus the area from a to just x for fu du. And let me move this down a row. I can grab it all there. If we want to find the area in just gray up here in the illustration, I can find the entire area, which would be the area from a to x plus h, and I can subtract off the area in blue, the area from just a to x. And that's going to leave behind that gray shaded area that covers over that length of h. That area over that length of h is given by the area function for x plus h minus the area function for x. All right. Now, that h is arbitrary. This value of h is arbitrary. And if we allow that value of h, that distance, to begin to shrink, as we begin to let it head to zero, get smaller and smaller and smaller, what you're going to see happen as h gets smaller and smaller and smaller, the actual area described by that region, given by this difference here in the previous step, in the previous note, is actually going to approach its own value. What it's going to approach in value is actually the value of h times f of x. H, the length of that interval that's heading to 0, times the height of that interval f at x. All right, let's go back and look at that picture. In fact, I might bring this down here just for the moment. Let's drop this below just to see it next to this. All right. This is what we've described to be the exact area here in gray. And as h heads to 0, right, this area in gray is actually going to approach the value of h times f of x. If we think about the shape of this region down here, that's in gray, the shape of that region is approximately rectangular in its shape. Right? It's not quite rectangular. We can see the top of it is curved. But other than that, the two sides and the bottom make it almost rectangular in shape. How do we find the area of a rectangle? Well, it's going to be the length of the base times its height. Now, what can we use to represent its height? Well, we can look at the value of x, and we can say it's going to be the output of the function f at that value of x. And that is what we've done up here, is we've said the area here is approximated by h times f of x. And what happens is h gets smaller, right? As the base measure gets smaller, the actual area is going to get really close to this approximate value. The approximate value is going to head to this area here, the exact area, but also the exact area is going to head to this approximate value. They're going to get closer to each other, we might think. Right? I wonder if I have a way of saying that here. trying just to see if I have a double arrow symbol. I do have right and left arrows. Arrow relations. Oh, I do. It's called the left-right arrow. I probably, by clicking on it, brought it down several times already. I did. So it's that arrow. These two values are going to head to each other, and we might show that with a double arrow. Let's do that. All right, let's do that there. Those two are going to get closer and closer and closer in value as h heads to 0. So what does that mean? Well, that means, if I get rid of that illustration here, this ends up implying that if I take the limit as h heads to 0 for this quantity a of x plus h minus a of x, it must be equal to then h times f of x as a limit statement. And as a limit statement of equality, I can shift this h from the right-hand side back over to the left by dividing both sides by h. And if I do that, I'll obtain this as my statement. 1 over h times the limit will end up equaling f of x, where that value 1 over h here on the left-hand side, right, it's not allowed to be out there as a constant multiple. It is actually the argument of h that is inside the limit, so it needs to actually be brought into the limit. It can't hang outside there. It has to be evaluated with the limit. So if I bring it into the limit, I'll end up having the limit as h heads to 0 for a cap a of x plus h minus cap a of x, all divided by h. I'll have the area function at x plus h minus the area function at x, all divided by h. And I'll be looking at the limit of that as h heads to 0. And I'm saying all of that equals f of x. And this value on the left-hand side should look familiar. We got to go back a few weeks, about 12 weeks to be exact. If you take a peek at that, that's the definition of the definite integral. The definition of the, careful there, not the definite integral, too soon, right? It's the definition of the derivative. It's been too long since we've said that. That is the definition of the derivative for cap a prime of x. Right? We say cap a prime of x by the definition of the derivative is equal to this limit as h heads to 0 for a of x plus h minus a of x all divided by h from its definition. And what we've just shown is that's all equal to f of x. The function, right, that's describing the curve that's trapping the area, right, that's described by a of x. And what we're linking to is the function that's trapping the area is actually describing the rate of change in that area. That's what a prime of x is, if you remember. That is the rate of change in the area. The actual function that traps the area under the curve, right, is describing the rate of change in the function that describes that area, a prime of x. So what we can do is we can go back to our statement for the understanding of the antiderivative, which says that the antiderivative of f of x dx, which would be equal to a of x plus c, since what we've just said is a prime of x is equal to little f of x, Or what I would be able to say is go in and replace this f of x with a prime of x and be able to say that the area function is really just the definite integral from little a to x for the rate of change in the area function. Right? The area function is really just an accumulation of its rate of change, right, over that interval from a to x. Right? This is connecting the antiderivative operation, the definite integral, to its derivative. Right? Or connecting the derivative to the definite integral calculation, which is really what we want to do. We know how to calculate derivatives. We don't need to bring out antiderivatives into their calculations. What we need to do is figure out how to calculate definite integrals. And what we're going to see is the antiderivative is going to be brought into those calculations. Excuse me. And what follows here is how to do that. What we say here, what we're showing is that the antiderivative of f must be related to a of x. Right? A of x is going to be the antiderivative of f. Those two things are related. The area function is related to the antiderivative of f. They only differ by a constant. Right? When we think about the area function and what would truly be the antiderivative of f, which we understand has also been denoted as cap f, because cap f's first derivative would also equal little f, has both a of x and cap f differing by no more than just a constant. Right? They are the same in value, except for a small constant difference. All right? Now, if we let a of x equal f of x plus c, let it be the antiderivative of f of x, or of little f plus some constant, then when we think about the area function at little a, the area function at little a is going to be the definite integral from a to a for f of u du, which we should point out is equal to the value of 0. Right? But because a of x is also equal to f of x plus c, a at little a can be rewritten as f at a plus c, cap f at a plus c. And likewise, if we think about little a or cap a at b, the area function at little b, the area function at little b is going to look familiar. It's going to be the definite integral from a to b for f of u du, which if a at x is equal to cap f at x plus c, then that's going to be equal to cap f at b plus c. So, what does that tell us? First of all, if the area function at little b can be expressed this way as the definite integral from a to b for f of u du, there's no reason why we can't change that dummy variable back to x and say that the area function at b is the definite integral from a to b for function f of x dx. Right? Because we no longer have to reserve x for that upper bound. X has been replaced by little b. Now, what else can we say about a at little b? Well, a at little b must be equal, can also be said to be equal to cap a at little b minus cap a at little a. Why I can just come in here and subtract cap a at little a is because what have we said it's equal to? Well, that's essentially equal to nothing. So what we'd be subtracting away here is nothing, which has zero effect, right? So stating that nothing is cap a over little a is perfectly all right because that quantity is equal to nothing. So if I have cap a at b minus cap a at a, and cap a at b is cap f at b plus c, and cap a is cap f at a plus c, cap a at a is cap f at a plus c, I can replace these two quantities in terms of the antiderivative of f regarding a and b, where we have this constant value of c as that common difference between cap a and cap f. And if I replace those, I'll end up with this statement here. F of b plus c, maybe I should throw that in brackets, minus cap f at a plus c. Where if I distribute this negative and drop the brackets, I'll have cap f at b plus c minus cap f at a minus c. Where that constant minus itself, zero away, become a zero effect. And we're left with cap f at b minus cap f at a. And there's the result we want. Take note, there's your definite integral from the previous section of material that we defined in the previous section. At the moment, we had to calculate that using a limit of a Riemann sum. What we now can show is that it's actually equal just to cap f at b minus cap f at a, where what is cap f? Cap f is the antiderivative of the function that we find in the definite integral calculation. If we go ahead and there's another way to write this. Letting f of b minus f of a, we can write that as this. Letting cap f at x evaluated. This is saying what we have here is cap f at x being evaluated across the bounds from a to b, which we're going to have that as an understanding of being cap f at b minus cap f at a. Then what we're able to say is that the definite integral from a to b for function f of x dx, that definite integral calculation that we've been calculating with geometry up to this point, or limits of Riemann sums, can actually be calculated using the antiderivative function cap f at x, finding its antiderivative using the formulas that we learned back at the end of chapter 4 and I won't let me date this. Back at the end of our study of the application of derivatives when we introduced the antiderivative. The antiderivative of little f is going to be cap f, and it's going to be equivalent to that definite integral when we evaluate it across the bounds from a to b. Which means we're going to evaluate that antiderivative at the upper bound of b and take away from its value the value of the antiderivative at the lower bound at a. Where again we understand that derivative of cap f is function little f, making it its antiderivative, right? Implying cap f of x is the antiderivative of little f. All right. That is also a result of the fundamental theorem of calculus. That is how we work through and calculate definite integrals. All right. We have proven all we need to prove for the the fundamental theorem of calculus, part 1 and part 2. There were two things that came out of this. The first was that if we think about the area function, because the area function exists, right, we can make a connection between the derivative of the area function and the function trapping the area, right? The function trapping the area is going to describe the rate of change in the area function. And when we think about the area function, it really is just an accumulation of its rates of change over the interval from a to the value of some arbitrary x. Right? Antiderivatives and derivatives are related through integration. By integrating a derivative, you will obtain an antiderivative, right? And when differentiating an integral, right, you'll obtain, well, when differentiating an integral or an antiderivative, you'll obtain a derivative. Yeah. We put this in other words down below here. Let me say it this way. In other words, there's a relationship between differentiation and integration where we might think of them as being inverse operations with one another. When they compose with each other, they undo one another. Derivatives applied to integrals will cancel the integral, leaving behind just the function in the integration. Or when integrals, antiderivative calculations are performed on derivatives for a function, they just cancel the differentiation, again leaving behind the function that was having the derivative applied to it initially. The two operations are inverses of each other and cancel one another. That's the first thing the fundamental theorem of calculus is telling us. The second thing it gives us is how to calculate its value. Here's the part 2. It says if we assume how to calculate the value of a definite integral using its idea, right? The area function. And it says assume y equals f of x is continuous over the interval from a to b. Then the definite integral from a to b for function f of x dx is going to be the antiderivative of f, that's cap f, evaluated across the bounds from a to b. Which means I'm going to take the antiderivative of my function f and evaluate it at the upper bound of b, and I'm going to subtract from it the antiderivative of little f being evaluated at the lower bound of little a. It's going to be cap f at b minus cap f at a. That's going to be the definite integral of f of x from a to b. The definite integral of a function across its boundaries from a to b is just the difference between its antiderivatives at a and at b. It's going to be the antiderivative f at b minus the antiderivative of f at a. That's what we put into other words here. Now, let's put this into practice. Let me go back and do some calculations for you that we've seen in the notes where we can apply this idea. Here's the first one. This should look familiar. What's this? This is the net area trapped between the square function over the values of x from 0 to 10. And we found this to be 1,000 thirds using limits of Riemann sums. Right? A little bit of rigor. Well, what we've just said above for this definite integral calculation is that I can take and just consider evaluating its antiderivative across the boundaries from A to B. Well, what's the antiderivative of x squared? Well, from the power rule, we know that's 1/3 x cubed. So if I evaluate 1/3 x cubed across the boundaries from 0 to 10, I'm going to start with the upper boundary at 10 and substitute it in here for x, and I'll have 1/3 times 10 cubed. And I'm going to take away from that, and this is what we're showing here, I'm going to take away from that the antiderivative of f, this quantity here, evaluated at my lower boundary of 0. So that's going to be 1/3 times 0 cubed. So 10 cubed times 1/3 will be 1,000 thirds, minus 1/3 times 0 cubed is going to be just 0, because 0 cubed is 0, and 0 times 1/3 is 0. So 1,000 thirds minus a 0 is just 1,000 thirds. The value we calculated earlier, or the value that we started to try to approximate at the beginning of the study using just Riemann sums, that we inevitably turned into an exact value when we defined the definite integral through calculating the limit as n heads to infinity for the Riemann sum of this approximations that we used, where now we just saw through the fundamental theorem of calculus and the use of the area function that I can calculate the definite integral of a function, this trapped area's value, using the antiderivative of that function by evaluating it across the boundaries from A to B. I can find the antiderivative of little f at B, and I can take away from it the antiderivative of little f at A. All right? That's exactly what we performed down here. One's a little messy. Let's see a little cleaner one. We also calculated this earlier on our calculator. Right? Remember, we went transcendental here with this. And we had to rely on our calculator because there was no way we were going to try to approximate this by hand using anything other than our calculator. And we found it was 1.9998 when we used 100 subintervals to calculate that. We said it was about almost 2. Well, look at what we get here. The definite integral for the sine of x from 0 to pi, right, is going to be the antiderivative for the sine of x. What's the antiderivative of the sine? Well, we know that's negative cosine. And we're going to evaluate that across the boundaries from 0 to pi. The boundaries on our definite integration. Which means I'm going to plug pi into this statement and find negative cosine of pi. And I'm going to take away from that what I get when I plug 0, this lower boundary, into this statement. I'm going to take away negative cosine of 0. I said this is a little cleaner, but not much. Look at all those negatives. Right? You got to watch that as you clean this up. The cosine of pi is -1. So I'm going to have the opposite of that as my first term. That's positive 1. I'm going to take away from that the opposite for the cosine of 0. Now, the cosine of 0 is positive 1. So its opposite is negative 1. And if I take that away, I'll be adding another 1. I'd have 1 plus 1 equal to the value of 2. And that is the value of the definite integral from 0 to pi for the sine of x dx. That value we had to use our calculator to approximate using n's equal to 100 subintervals. And that we would really have to approximate if we were using subintervals, our calculator to approximate for subintervals when we were using anything other than those multiples of 30 or 45 degree angles. Where from 0 to pi, there's only 3, and they don't really subdivide anything. Right? I guess we could use 30 and 60, and we could subdivide that interval into 3 equal pieces. And that's about as exact as we could get without using our calculator. Well, now we have a method to find it exactly. It takes very little rigor and just relies on us knowing the exact trig values at the boundaries, 0 and pi. Right? Here's another one we did earlier when we were studying area function. Right? We had defined what the area function for the area trapped between the line, or trapped by the line, 1/2 u plus 5, over the interval from 2 to x being an arbitrary upper bound, the independent variable in the area function. Well, what we just learned through the definition of the definite, or through the use of the area function to give us the fundamental theorem of calculus part 2, is that I can evaluate this definite integral by using its antiderivative. What's the antiderivative of 1/2 u to the u plus 5? Well, this u goes up by a power, goes up to 2, and then we divide by 2. So 1/2 divided by another 2 is going to give you 1/4. This 4 is that 2 times 2 in the denominator. And the antiderivative of a constant is just going to be 5 times the variable of the integration. That constant times the variable of integration, 5 times u. So here's my antiderivative of this linear function. It's this quadratic function. And I'm going to evaluate it now at the upper bound. I'm just going to plug in x for each of those values of u, and I'm going to take away from it what I get when I plug in 2 into each of those values. And notice what happens. When you plug in x, you'll get 1/4 x squared plus 5x when you substitute this upper boundary into this antiderivative. And you're going to take away from it what you get when you substitute in 2 into this antiderivative. Now, this first term will be 1. 2 squared is 4, divided by 4 is 1. And you're going to add that to 5 times 2, which would be 10. 1 plus 10 is 11, and all of that is subtracted from this quadratic. So the end is 1/4 x squared plus 5x minus 11. Look back to the area function, our example back in the area function where we encountered this case. That was the function we found using geometry. Remember, we did this calculation in just the previous video, right at the end as an example, where we used geometry to find this function. Well, here I now, this time around, I use the fundamental theorem of calculus part 2 and the antiderivative function. Let me give you one more. And we're going to be practicing this a lot now. This is kind of how we're going to end. There's a little bit of practice, more practice with this. And then there's one more advanced rule we have to talk about. And that's how our semester ends. But I'll say here, consider evaluating this. The definite integral for 3x squared plus 8x minus 10 for this quadratic, evaluated across the bounds from 2 to 5. Right? Well, across those bounds from 2 to 5, we're going to find the antiderivative of 3x squared plus 8x. This is a polynomial. You should be able to evaluate polynomials pretty quickly here. That's why I've kind of stuck with these examples for these first few initial cases. 3x squared's antiderivative will bump up to 3 in power, and we'll divide this all by 3. Well, that dividing by 3 will cancel with that 3, leaving you with just x cubed. Right? If I bring the result up, we'll start to see that. The first term in the antiderivative coming from 3x squared, its antiderivative is simply x cubed. 8x's antiderivative is 4x squared. We bump the power up by 2, but then we divide 8 by 2, and that's where we get the 4. And then the antiderivative of the constant 10 becomes the constant times the variable of interest in our definite integral, the variable x. So what I end up with is x cubed plus 4x squared minus 10x, where I have to evaluate that across the boundaries from 2 to 5. Starting with the upper boundary at 5, I substitute that into this polynomial, and that gives me this result here. And if I do the math there, that becomes 125 plus 100 minus 50, which ends up being 175. And I take away from that what I get when I substitute 2 into this value. If I substitute in the 2 into x cubed plus 4x squared minus 10x, I'll have 2x cubed plus 4 times 2 squared minus 10 times 2, which will be taking away 2 cubed is 8. 4 times 2 squared is 4 times 4, which is 16. And 10 times 2 we know is 20. So I'll have here 24 minus 20, that'll leave behind 4. So I'd be subtracting at the end here the value of 4. So what's 175 minus 4? It's 171 in value. The net area trapped between this curve, right, 3x squared, the parabola, 3x squared plus 8x minus 10, over values of x from 2 to 5, is 171 units squared. All right? The value of this definite integral calculation is 171. All right? That's the end of my notes here for Fundamental Theorem of Calculus, folks. This is a few examples actually putting part 2 into use. Part 1 just really makes a connection for us. It says derivatives and antiderivatives are inverses of each other. They cancel one another when composed with each other, is what part 1 says. Part 2 gives us the way to calculate our definite integrals using our antiderivatives. Right. Part 2 says the definite integral of f of x from a to b is just the antiderivative of f evaluated at b minus the antiderivative of f evaluated at a. This middle step here, this is just a way of organizing your work so that you can make note of what is the antiderivative before you have to evaluate it across these boundaries. It's useful to have this noted before you consider plugging in those numbers. So this middle part of the equality, that middle expression in this equality statement, is used to be able to bring out and talk about the antiderivative as part of this calculation. That's the fundamental theorem of calculus, folks. We're going to come back in the next video and I'll do a bit of a summary because, truth be told, the definite integral, the integral from a to b for f of x dx, we have said means a few things now. Quite a few things. So we're going to go through and we're going to summarize all that. And then we're going to get a little bit more into the properties and calculation, and we'll go through some more examples of calculation. And then we're going to finish the semester with one advanced technique for finding definite integral calculations and calculating antiderivatives. A technique known as what? Variable substitution, or you'll sometimes hear me say U substitution. All right. But with that said, we're at over 45 minutes for just fundamental theorem of calculus. It's, again, really another late night for me here. So I'm going to end the video here, and I'll come back with what is going to be 2 more videos this semester to begin wrapping up the topics that we study here in Calculus 1. All right, folks? So I will see you in class and see you in the next video.